Hey guys, I have your notes here for day 2 of antiderivatives. And again, you're just kind of getting used to taking some simple antiderivatives, finding that original function. Don't forget to put plus c on the end of it because we don't know what that constant was. And then we'll also get into looking at, the graph of a derivative. What does that look like for the original function? And then some word problems. All right, so here we go. I've already filled out some of them for you, just some things that I want to point out, and then we'll work out the problems together. I don't remember how your paper is set up, but I'm going to start with example 4 on mine. It's the one where you're given 2 points. That's the one I'm going to start with. It's a polynomial, so it's going to be a very simple antiderivative. So we're given, this is the derivative of f, it's a polynomial, and we're given some extra information. So this right here gives me 2 ordered pairs on the function f, which we don't know what the function f is right now. So this is specific information for f, 2 distinct points. Here I go. I'm getting ready to take the antiderivative of this. So since it's called little f prime, I'm going to call the antiderivative just little f. All right, here I go. I'm going to power rule it. I'm going to raise it and divide. Raise it and divide. Throw an x on it. Don't forget plus c. This is called the general antiderivative because it's got the plus c on it, and at this point we don't know what c might be. And then we're given some specific information on f. Hang on, let's label this the general, these vocab words are going to come in handy later. The general antiderivative. Because it's got the plus c on it. Okay, so to find f, to find c, so that we know exactly what f is, we're going to use a point on f. And you can use either of these 2 points. I kind of like 0 the best, having an x value of 0. So I'm going to sub in 4 for y and 0 for x. All right? Gone, gone, gone. C is 4. So, f specifically is 4x cubed minus 3x squared minus 4x plus, now we know, that constant, which was plus 4. The cool thing about polynomials and given a point, 0, whatever, is when you do an antiderivative, you often think of this last constant term as your y-intercept when x is 0. So again, this is just for polynomials. Don't make this generalization for trig and exponential and all these other functions. But for polynomials, when you're given your y-intercept, yeah, that's pretty much automatically that constant value back there. Okay, the next one that I want to do with you is number 3. This one's a little more tricky. So again, same setup, only this time it's not a polynomial. I'm given the derivative, and I'm given 1 point on f. So before we start taking the antiderivative, this part's going to be easy. So when I take the antiderivative on this term, super easy. This one, not so much. This isn't 20x to the negative 1. So you can't just say, oh, well, the antiderivative of 1 over x is natural log. No. This isn't just a plain x. This is something messy being raised to the negative 1 power. So I'm going to do a quick rewrite before we start our antiderivative. So f prime also looks like this. I'm going to slide So this is basically under the 20, and I'm going to slide them apart. So 20 is like my coefficient of this term. Does this look familiar? Does this look like the derivative of anything you kind of, sort of, maybe remember? This is the derivative of tangent inverse. Remember that those 6 trig inverse derivatives that I said, oh, for your final or whatever, you don't have to memorize those. And you kind of don't, but the most common one is tangent inverse, which, lucky for you, is the easiest one. This is the cleanest one. It's the cleanest of all 6 of those derivatives. So this is the derivative of tangent inverse. 20 is just the coefficient that's out in front. All right, so let's do this antiderivative. That part was easy. Remember, this fraction is the derivative of tangent inverse. So when you do an anti, that's what you get, plus your constant. If you're gonna remember any of the 6 of them, remember this relationship. Okay, we're gonna find C. So I'm going to use a point on F. And I'm running out of room. So 20 is equal to, let's see, e to the 0 is 1. Now, this is going to be 20 times something. So when we are evaluating, my bad, that's a 2. I carried that forward wrong. 2 is equal to e to the 0 is 1 plus 20 times something we don't know yet plus c. There we go, that's better. All right, when you're evaluating trig inverse problems, remember this, if it's not an inverse problem, this is the spot for your angle. And your answer is always your fraction. On an inverse, it's backwards. They're swapped. This is your fraction. Your answer needs to be your angle. So here's the question. What angle? What angle? From 0 all the way to 2 pi. What angle has a tangent fraction of 0? The angle that has a tangent fraction of 0 is 0. So C turns out to be 1, and F is e to the x plus 20 tangent inverse of x, oh dang, I'm out of room, plus 1. This is, remember, this is what we call the general antiderivative because it's got the plus c on it. This is the particular antiderivative that passes through that point. General, particular, that passes through that point. Righty, moving on. Again, don't hesitate to pause the video, catch up with your writing, catch up with your processing. This is the foundation of everything that's going to happen second semester, or at least third 9 weeks. All right, here we go. Let's take a look at this. This is the graph of the derivative of big F. These values, negative values, positive values, negative values, these show the slope of big F. we're going to draw big F. All right, so we're going to look at slopes here. Since these y values are negative, big F is going to be decreasing. These y values are positive. Big F is going to be increasing. These y values are negative. Big F is going to be decreasing. Negative, almost 0. These y values, again, show the slope of big F. Big F is still going to be decreasing. But the slope of big F is going to be almost 0. So it's decreasing, but it's leveling off. Here, slope of 0, slope of 0. Big F probably has a peak or valley here. When my derivative of big F is 0, I think there's a peak or a valley, and we can pretty easily tell which one it is. Big F was decreasing. Big F was decreasing. Big F has a slope of 0. Big F is increasing. So there's a valley here. Big F is increasing. Big F has a slope of 0. Big F is decreasing. There's a peak here. Okay, let's draw it. And, hang on, a little bit more information. We have a specific starting point. All right, this tells us exactly where to start. Otherwise, I can do the whole decreasing, minimum, increasing, peak. I can do that, but I would have no idea where to start. How high or how low would it be? We wouldn't know, except we do now because now we have a starting point. So starting here. Now this is the only point we know. So this is the only specific that we're going to know. So from here, let's start decreasing. Let's valley somewhere. I don't know how low. I don't know how low to go. But let's have a slope of 0 when x is 1. And then let's start increasing. We're going to increase until x is 3. And then we're going to peak. And then we're going to start decreasing, and level off. Okay, so we're going to decrease until x is 1. And then we're going to have a slope of 0. Increase until x is 3, and then we're going to have a slope of 0. And then we're going to decrease, level out. I don't know where, but I need to show that it's leveling out. And I didn't want to level out close to 0 because just because the slope is getting close to 0, all that tells you is that this graph is leveling out. It doesn't tell you this graph is getting close to 0. It's saying the slope of the graph is getting close to 0. So I kind of didn't want to level out up here only because I didn't want you to think that it has to be approaching 0. The graph doesn't have to be approaching 0. The slope of the graph has to be approaching 0. Alrighty, fun stuff. Moving on. Whew, this is where I need you to use your brain. So I need you to be able to read a problem, pull out information that it's giving you, and know exactly what it's telling you. and read and interpret what the problem is asking. You have to know what the problem is asking you to do. So, we're going a particle, straight path, okay? We're given an acceleration function. Remember how it goes position, velocity, acceleration. We're given the acceleration function. Initial velocity is v of 0 equals -6. This is a point on v, not on a, not on s. It's a point on the function v, 0, -6. Note that it's also called its initial velocity. Initial means at time 0. When we start this experiment, initial velocity at time 0. Initial displacement. Know that displacement and position function go together. The displacement and the position function go together. So this is a point on S. It can be called its initial displacement, or it can be called its initial position. Vocabulary. Lock those in. You're going to have to interpret those words over and over and over again. So I'm going to write my acceleration function, 6t plus 4. I'm going to do an antiderivative on it. Now, it would be kind of weird. I mean, you could, but it would be kind of weird to do an antiderivative on acceleration and call it big A. I mean, if we're looking at acceleration and we're doing an antiderivative, let's call it v. That makes so much sense. We're going to raise it and divide. Throw a t on there, plus c. That's your general antiderivative for velocity. That's weird. Why do I have two equal signs? We're going to use a point on v. Or it's a polynomial. You can say that you know that when you put a -6 here, and that becomes 0, and that becomes 0, c is -6. So v is equal to 3t squared plus 4t minus 6. Let's do an antiderivative on that to get our position function. Raise it and divide. Raise it and divide. Throw a t on there, plus c. And then somewhere, where'd it go? We have the initial position, so when t is 0, s is 9. This is 9, 0, 0, 0, c is 9. Okay, let me just double check that that's what it said to do. Find its position function. Did that. It's not the general one, it's the specific one, because we found what its initial position was. So, if you wanted to know where was this thing at 6 seconds, plug in a 6 to find out where it was. This is its position. All right, last one. Again, I've kind of already highlighted the important information. I need you to pay very close attention, vocabulary, be able to interpret. So, someone is throwing a ball straight up in the air, speed of 48 feet per second. I need you to realize, oh, hey, that's my initial velocity. Throw a ball straight up in the air, initial velocity is positive 48. You know what's going to happen to the ball. It's going to go into the air with an initial speed of 48, but as it rises, the speed is going to decrease because you know it's going to slow down, peak, and then start falling. So it's going to have a positive velocity until it reaches its maximum height, and then it's going to start having a negative velocity as it starts falling. All right, it's thrown from the edge of a cliff. The cliff is 432 feet above the ground. This is its initial position. Here's what you're supposed to do. Find its height. Position. Find the position function in terms of t. When? Time. When does it reach its maximum height? So at what time did it peak? How many seconds did it take for it to reach its maximum height? And then the last question, when? Solve for t. When does it hit the ground? When is its position, its height, 0? Okay? Now, well, let's go with that. So these three things that I just highlighted, I've kind of put it in words that you might understand a little bit better. Find its, hold on, if I can have good grammar, there we go. Find the height or the position in terms of t. So basically we're going to find the s function. Find the time, find the time. Thing is, we don't have a place to start. We weren't given a function. See, up here, we were given an acceleration function. We're like, oh, hey, let's do an antiderivative. Oh, hey, let's do another one. We don't have a function to start with. But we kind of do. So if no function is given, let's just start with the fact that we know that the Earth's natural acceleration function is gravity. And I know you've been in enough science classes. You know that the pull of gravity is a constant. It's a pull downward, so I'm going to associate that with a negative acceleration. It's a downward pull. It's constant. I know there are other factors involved, but we're not taking any of those other factors into consideration. So, this might be a good thing to memorize. In English units, acceleration is a constant. It's negative 32 feet per second squared. Negative 32 feet per second. Or in metric units, it's negative 9.8. Notice I put a negative on it because it's a downward pull. Meters per second. Every second. All right, what are we on here? We are in feet per second, so we are going to use the English units. Might seem kind of weird to you that I'm writing the acceleration function in terms of t, but all I have is a constant right now, so I'm declaring when I do my antiderivatives, t is going to be the variable that I'm going to use. Antiderivative. I'm going to use the fact that v of 0 is 48. There's my velocity. There's my specific, not general, my specific velocity function. Let's keep going. Let's do an antiderivative on that. I'm going to raise it and divide. Throw a t on there, plus c as my constant. Remember my initial, the ball's initial position was 432. S of 0 was 432. There we go. That's your position function. In fact, I think that's the answer to one of our questions. Is that the answer to one of our... Find its height, find its position, t seconds later. We did that. So I'm going to highlight that in blue just because I have answered the blue question. Next question, green question. When does it reach its maximum height? Let me give you two options. Option number one, upside down parabola. You can do its, what is that called? Vertex. You can find the vertex of this parabola. Or, when it reaches its maximum height, so it was thrown upward at a speed of 48, slows, 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 slows. When it reaches its peak, its velocity was 0. I like that one. I'm going to find when the velocity was 0. So let's see, I'll just keep going. No, I'm going to come up here. There we go. When the velocity is 0. Took 1.5 seconds to reach the maximum height. Last question. When does it hit the ground? When does it hit the ground? Some of you, there's one correct way to do this, and there's probably more than one incorrect way to do this. When the ball hits the ground, don't you agree that it started at a height of 432? It went higher, and when it passes back below the cliff and actually hits the ground, the height is going to be 0. When it hits the ground, its height, its position is going to be 0. Some of you are going to say, oh, well, also when it hits the ground, it stops, so its velocity is 0. The only reason its velocity is 0 is because there was a ground there. Because otherwise, really, the velocity, when you look at it from an equation standpoint, the only time that the velocity could be 0, the only time that the velocity could be 0 was when it reached its peak. If the ground wasn't there, it would just keep going and going and going and going and going, and it would never again have a velocity of 0. So use the fact when it hits the ground, use the fact that we want its position, its height to be 0. So I'm getting ready to, when s of t equals 0, this is going to answer when it hits the ground. So I'm going to, yeah, that was orange. On my paper, I tried to factor it, so I was able to pull out a -16. I really wanted to factor this. -16 t squared minus 3t minus, that was a 27. And I saw the 3 and I saw the 27, and I'm like, ooh, I can do this. Turns out, no, I couldn't do that. That's not factorable. So I had to use my quadratic formula. So I used quadratic formula. And I got And I should have rounded to 3, but I didn't. So I got 6.9 and I got negative 3.9. And some of you are very insistent that, hey, these are the two solutions. These are 2 times that it could have hit the ground. Don't let your time be negative. Don't let your time be negative. Took 6.9 seconds for it to hit the ground. Again, round to 3 usually. I'm not sure why I didn't, but there you go. Okay, again, if you need to rewind and go back and listen to me interpreting this and kind of writing down what it all means, it is so important that you're able to read and interpret, pull out the information in the problem, and be able to figure out what it wants you to do. Alrighty, good luck.